Till now we have seen only square waves. Okay, many of the people will have the confusion in frequency of these kinds of waves. So here see, and even these lights which are running on electrical current, AC current, these are also flickering, right? These are also flickering at around 50 hertz or something, and you do not see the effect, you do not see it flicker, right? If we go on to calculating how much the width we need for the counter, we will have this calculation. So let's do the calculation. Time period of one cycle is equal to this. If we multiply with x number of cycles, we'll have the original time period, and the original time period we require is 20 milliseconds. We know that as soon as our counter reaches this 1 million mark, we are going to toggle the LED from 00. If we go to 01, if you see, this is around 20 milliseconds, which is close to 25% duty cycle. So 5. Hello everyone, welcome to day 22 of the 100 days of FPGA series. In this video, we will be covering pulse width modulation, and we will be generating PWM signals from our FPGA. Okay, so let's first understand what is a PWM signal. Okay, so a pulse width modulation, basically we control the width of the pulse. Okay, what that means is that till now we have seen only square waves. Okay, when we were toggling LED, in previous videos, we were generating square waves, right? We used counters to slow down the faster clock. Like we used the counter for basically toggling the LED after a certain number of original FPGA clock cycles. Okay, and that generated a square wave because we were toggling the LED every, like, in equal periods of time. Like we were basically flipping the LED on for 1 second, off for 1 second, on for 1 second, off for 1 second, and that means that the on period and the off period were exactly the same, and that will produce a square wave. Okay, so the wave over here which I have drawn, this is the square wave. Okay, here the frequency is this. So whenever you calculate frequency, you calculate one wave. Okay, so for one wave it would be this. A wave will start with the high period and with the low period, and this equal section is the time period of the signal. Okay, here the t on period is same as t off period. Okay, so time when the signal stays on and time when the signal stays off is exactly the same, and that will produce a square wave. Okay, but when we vary the width of the pulse, we can basically generate these kinds of waves. Now many of the people will have the confusion in frequency of these kinds of waves. So here see, if you see these kinds of signals in reference to the square waves, you will see that the frequency is exactly the same of both of these signals. Okay, both of the signals are repeating after same time period. Okay, if you say this is the structure of this wave, and it is repeating, like this structure repeats, and it repeats after same number of same time as the first signal, right? So the frequency of these two signals are the same, and that is one thing that you need to keep in mind. There is a frequency of PWM signal as well, and that frequency is this frequency. Okay, so do not confuse, like many of the times people confuse this when they see non-symmetric wave. People kind of confuse it, what the frequency will be. Okay, frequency will be the same only. If you see the total t on and t off time, if you add these two, that will be the total time period, and the frequency will be 1 over the total time period. Okay, so this here over here, if you see, the t on period over here is less than the t off period. Okay, so the signal remains on for lesser amount of time in its duration. Okay, in one time period. Okay, and here if you see this green signal, it remains on for a longer period of time than the previous two signals, and if you see, it goes down just for this amount of time, roughly 1/4 of the time it is off. This is roughly on for 1/4 of the time, right? So how do we calculate the duty cycle? What is duty cycle? It is the t on period over the total time period. Okay, and the total time period of a wave is t on plus t off. Okay, you do not need to learn this formula to understand PWM. I'm just written this so that you can understand duty cycle. Okay, and usually you basically have expressed this in percentage. Okay, so what percent of the time the signal is on is the duty cycle of the signal. Okay, so coming on to this, if you see the duty cycle of the signal, if this is on for 1/4 of the time period, you can simply say that its duty cycle is 25%, and here it is off for 1/4 of the time period, that means it is on for 3/4 of the time period, right? So in that case you will have 3/4 into 100, which will be 75% of the duty cycle, okay, of this signal. So the frequency, do not get so the main important thing in here is do not get confused in frequency, okay? Frequency of all these waves are the same, okay? In PWM also you have the frequency, and we can calculate two things in PWM. So we'll be calculating the frequency and we'll be calculating the on period of the signal, on and off period of the signal, okay? And we'll be toggling the signal on and off depending on how wide we want the T on period, okay? Now there are various uses of this PWM signal. You can find these signals in controllers like RC controllers and all. You can have the servo motors, that those servo motors are controlled by the PWM signals only. Like many of the servo motors are controlled by PWM signals. Many of the RC plane transmitters and transmit, and the receivers receive in PWM only, okay? So usually they would have a PWM signal output and IBus output as well. So that this PWM signal is very important in communication as well, okay? In digital communication it is really important. So many people, what they do is they can even convert analog signal in transform it into this PWM signal, and they can basically on the receiving side have a envelope detector kind of a circuit, and they will basically track the PWM signal, and that will basically give them the analog signal back. So you can digitally transform, like many of the amplifiers as well, the audio amplifiers do that kind of thing. Here in today's video we will be understanding how we generate this using our FPGA, okay? And we'll be controlling an LED with it, okay? Now I would like to discuss the application of this PWM on the LED, okay? So if you see the T signal, the T on period is basically this duty cycle, okay? So the in PWM signal we can vary the amount of time the signal stays on. If you attach an LED over here, it's two terminals, and let's say this is the anode, and if we simply attach it to this signal over here, and if we just ground it, now if you see, this LED will be glowing when the signal is high, right? The signal is high in this period, so the LED will be on for this period of the time, and the LED will be off for this period of time. Now if you have the frequency too less, okay, if you have frequency, let's say this entire period is 1 second, okay, and it is on for 3/4, which is 750 millisecond, and it is off for 250 millisecond, you can easily notice it's on and off period, okay? So you will see it flickering. It will be on for slightly longer, it will be off for slightly lesser amount of time. So that is not interesting, right? Once we have the frequency high enough, we will be not able to differentiate that flicker, right? We have discussed about this in the previous videos as well. In the blinking LED circuit encounter, we have discussed this thing. Like when you increase the frequency of the light, it will not be seen by the human eye, right? If you basically flicker a light fast enough, you will not be able to see it flickering, right? And even these lights which are running on electrical current, AC current, these are also flickering, right? These are also flickering at around 50 hertz or something, and yet you do not see the effect, you do not see it flicker, right? When you have the slow motion in your phone on, you will be able to see it flickering, right? So that those lights are also flickering, but yet you do not see it through your eyes because they are flickering very fast, right? So here also, if this signal, this will be flickering very fast, you won't be able to notice, but you will see the effect, okay? Even if you do not see it going from high to low to high, you will still feel the effect of it being high for a longer amount of time and low for a shorter amount of time, okay? What I mean by that is let's see, you do not see the flickering effect, okay? But still the LED is off for quite a long time, right? The brightness of the LED is because it is on, okay? If you have a constant DC signal going into that LED, you will have it on for 100% of the time, right? And that will be the 100% brightness, okay? But if you have the LED on for only 75% of the time and 25% of the time it is off, that means you are basically seeing the averaged out brightness, okay? Because since you are not able to perceive the flicker, you still will be able to perceive the brightness, okay? Because it is on for longer and it is on for some time and it is off for some time. Okay, similarly here as well, if you see, it is on for this amount of time and this long period it is off. Okay, so that means only this amount of time it is giving out light. Okay, and since you cannot notice the flicker because of the frequency, you will be basically having the effect that it is its brightness is lowered. Okay, we will be putting it on the LED as well and we will see that. Okay, so enough of this theory, let's get into Verilog and design this PWM generator. Right, so I'm in VS Code right now, and let's create the module. So I'll create a module PWM. In the input of the PWM generator, I will be having let's say clock and reset, and in the output I'll be having LED. Okay, so let's have the output as LED, and what we require is to generate this periodic signal. Okay, so any periodic signal, even in the LED blink example we had seen, we had used a counter. Okay, so here as well we will be using a counter. So let's see the logic first. Okay, for defining the counter, the first thing that we need is to calculate the frequency, right? The counter here will act as a cycle counter of the original FPGA clock, and will be toggling our output, this PWM output, based on this counter. Okay, so here if we select a value, let's select 50 hertz. Okay, let's select a frequency of 50 hertz, because 50 hertz I think we should not be able to see the LED flickering and the LED will look continuously on. Okay, so that's why I'm selecting 50 hertz. If we go on to calculating how much the width we need for the counter, we'll have this calculation. So let's do the calculation. So we need to flicker our signal at 50 hertz. Okay, so 50 hertz means we need to have the time, we need to calculate a time period. Okay, so if we have the time period of our signal, it will be 1/50. We need to have a counter that can count up to 20 milliseconds. Okay, what I mean by count up to 20 milliseconds, see, our FPGA clock is 100 megahertz. Okay, at least the one I am using. Okay, that is 100 megahertz. So FPGA clock is 100 megahertz. I have to basically calculate and track time by using this clock. Okay, that is the logic that we are going to use. So we'll have a counter that will count number of cycles of the FPGA clock, number of cycles that have passed. Okay, and for 20 milliseconds we need to calculate how many cycles we need to count of the original FPGA clock. Okay, if you are not understanding this original FPGA clock and counter thing, please go ahead and watch the LED blink example that I had shown in previous videos. Okay, there I have explained this in very detail. Okay, if you have that idea, you will be able to understand this very clearly. So let's see what is the time period of this. This is 1/100 megahertz, which is going to be 1/10 to the power 8 second. This is the time period of the original FPGA clock. Okay, now this is the logic. See, if we have this as a time period, this is the time period of one cycle of the clock, one cycle of the FPGA clock. Okay, from here to here. So if we have x number of cycles, we'll have one time period of one cycle is equal to this. If we multiply with x number of cycles, we'll have the original time period, and the original time period we require is 20 milliseconds. Okay, so 20 into 10 to the power minus 3 we require, right? So x, which is the number of clock cycles that we need to count in the original FPGA clock, so that we count 20 milliseconds, is going to be solved through this equation. So if you calculate x from here, you are going to have 20 into 10 to the power minus 3 multiplied by 10 to the power 8, right? So you'll have this as 10 to the power 5, and this is 2 into 10 to the power 6. This is 2 with 6 zeros, right? If we count this many cycles of the original FPGA clock, we are going to count 20 milliseconds. Okay, this is the logic. So let's have that counter, and for counting these many this long of a number, how many bits we require? I've discussed it earlier as well. We require log base 2 of this number, right? So if you calculate 2 to the power of any number, let's start with, I know that 2 to the power 16 is 65,535, so it is, this thing is greater than that, so I would say 17 or 18. Let's go with 20. If we have 2 to the power 20, we'll have this number. Okay, we have 1048576. just for the 20 bits. Okay, so if you say this is 1 million and this is 2 million, okay, so still we cannot count that long. Okay, so we need 21 bits, I think. So let's go with 21 bits. So if you calculate 2 to the power 21, you should have sufficient amount of space for 2 million. Okay, counting 2 million, right? So let's code it in here. We'll have a counter which will be of 21 bits long. Okay, based on this counter, we need to basically toggle the signal high or low depending on how much of a duty cycle we want. Okay, I'm going to pick a few duty cycle that I'm going to implement in this module only. Okay, and so let's pick a duty cycle of 100%, 75%, 50%, and 25%. Okay, 0% will have the LED off only, so let's not do 0. Let's have these four duty cycles programmed in our FPGA. And how do we select the duty cycle? Let's select the duty cycle using switches. Okay, since on our Nexus FPGA board we have lots of switches, we'll use 2 of them. Okay, because using 2 of them I'll be able to map it on the switches, right? I can map this on the switches, and therefore we'll have lots of different PWM signals to compare it from. Okay, in a single design. Okay, so if we go in here, what I'm going to do, first off I need to run the counter. And in the reset condition I'll set the, otherwise what I'm going to do, I'm going to count on the counter, I'm going to increment the counter. Okay, but we are not incrementing the counter indefinitely, right? We are incrementing till we reach this point. Okay, so from 0 to 2 million minus 1 we are going to count, and as soon as we reach this 2 million number, we are going to reset the counter, right? Then we will be able to constantly track that 20 milliseconds. Okay, so if the counter let's say it is less than 2 million, then what we are going to do, if it is less, I'm going to increment it, right? And if it is not if it reaches this number, I'm going to simply reset the CTR. In fact, it is better to have this number in a parameter, but I'll explain about parameters in the next video. Okay, then I will put this this 20 million or 2 million in the parameter, and then we can easily change the time period and everything. We'll discuss about that in the next video. Okay, so right now this should be fine. We are constantly going to generate a signal of 50 hertz. Okay, this counter is counting 20 milliseconds, and with respect to the value of the counter, I'm going to basically vary this duty cycle. Okay, for giving you a quick intuition, I'm going to set a simple 50% duty cycle example. This is square wave example. Okay, so how do we track this 50% duty cycle? We need this signal to be high for 50% of the time, right? The entire signal is 20 milliseconds, so we need the signal to be on for 10 milliseconds, right? We need the signal to be on for 10 milliseconds, and 10 milliseconds if we count using our counter, 10 milliseconds will correspond to how much? You need to think about that, right? See, 20 milliseconds corresponds to 2 million, so 10 milliseconds will correspond to 1 million, right? So it will correspond to 1 million in our counter. So we know that as soon as our counter reaches this 1 million mark, we are going to toggle the LED or set the LED high for that much period of the time. So you can imagine counter going from 0 to 1 million, and then from 1 million to 2 million, and from 2 million it will be resetted back to 0, right? So from 0 to 1 million, if I see that the counter value is lesser than 1 million, I can simply set the output as 1. And if I see that the counter value is between greater than 1 million and less than 2 million, I can simply set the output as 0. And that will basically give me the square wave output, equal T off and T on time, right? This is an example intuition. Let's get that intuition for these other duty cycles as well. Okay, let's talk about 100% duty cycle. 100% duty cycles means that the signal is constantly on, right? It is on for 100% of the time. Our counter is counting up from 0 to 2 million, right? So if we have our output as high until the counter reaches 2 million, we are going to have a 100% duty cycle, right? Because the counter will reach it at 2 million and will again go back to 0, right? So if we have our signal as 100%, we can simply set the set that mark of the counter at 2 million itself, right? That is the intuition. Let's go and see this 75%, okay? There are two ways in which you can think of this. You can calculate from the starting that 75% of the duty cycle will mean how much of the time, okay? So 20 millisecond pulse is there. If we have it on for 75% of the time, that means we are having it on for 75 over 100 into 20 millisecond, right? 3 over 4, right? And this is 5, so this is 15 millisecond. So the signal is on for 15 milliseconds and off for 5 milliseconds because the total time is 20 milliseconds. Alright, so but we do not have this 15 milliseconds being given to us from the FPGA, right? We need to count and we need to track the counter, okay? So after 15 milliseconds, at that mark, where will the counter be, right? We need to find that, and we can simply plug this 15 milliseconds over here, right? If we have, and we can simply count the number of cycles that will pass in 15 milliseconds, right? So if we have x is equal to, this is going to give 15 into 10 to the power minus 3 into 10 to the power 8, and this is simply going to be equal to 15 into 10 to the power 5, which will give you 1 5 and 5 zeros, right? 1.5 million. Okay, so if the counter reaches 1.5 million, right? If the counter over here going from 1 million to 2 million, we will have 1.5 million as well, right? So we will have the output set and high until the counter reaches up to 1.5 million, right? Then we'll have a 75% of the duty cycle. Okay, this is the logic. Similarly for 50%, okay, 50% we have already seen, we need 100,000. If we calculate for 25, you can again basically calculate for how much time it is high. Okay, we'll have this 25 over here, that means it will be high for only 5 milliseconds, and we can again plug this in here and get the output of how many clock cycles will the counter count until it has passed 5 milliseconds. Okay, otherwise what you can simply do is, you already know that the counter basically goes from 0 to 2 million, right? This is the 100% of the time period. So for 50% of the time period, the counter will be at 1 million, right? Other thing you can do is, for 25% and 75%, you can, this is the half of between these, right? So this will be 1.5 million and this will be 0.5 million, right? So you can simply perform your percentage on this number as well, 2 million as well. Okay, so these are the two methods you can basically do. Both of them are logical. We are calculating, we are tracking the time with the help of counter. Okay, so the counter values that the counter will output, that values we will take and we will see if the time has come to get the LED high or get the LED low. Okay, that will be our logic. Okay, so now in here, since I'm going to implement all of these, I need to have a decoder circuit for the switch as well. Okay, so I'll have the input as switch, and in the switch I'm going to have 1 down to 0. I'll use 2 switches because I have 4 combinations. Okay, and I'll use an always block. Before we incorporate this switch, even though I have declared it, before we incorporate this switch and basically generate any of these 4 signals using the single logic, I'm going to generate a 50% duty cycle signal so that we can get the feel of how it is generating. So I'm going to have a variable name as duty, and this will be the counter value for which we are waiting. Okay, until we are pulsing high. Okay, we are waiting for a certain counter value, right? Until we'll drop our signal to low. Okay, so that counter value we need to store this in this duty register. Okay, so here this also will be same width, because our duty variable we can wait for entire 2 milliseconds, 20 milliseconds as well, so we need to have the full range for this variable as well. So here, and I'm going to set this duty as equal to, we are doing it for the 50% of the duty cycle, so let's put this duty as 1 million. Okay, so I'm going to write 1 million right? Here the logic what we can write is assign. Now let's have a signal, let's also output a signal which is called as PWM out, okay, and we'll assign this PWM out is equal to this logic. So if the counter is less than, our threshold, right, if the counter is less than our threshold, we are going to have it 1, okay, we are going to keep it 1, okay. So what we are doing is we are keeping it 1 until we reach a threshold, right, until we reach a threshold. So that threshold is basically what we have calculated, right. So until we reach that threshold, we are going to have that as 1. Otherwise what we are going to do, once we cross that threshold, we are going to have it as 0, okay. So this is the logic. So if you see the program flow, this counter is going to start counting from 0 and it will stop counting at here. Once it reaches 2 million, it is going to basically be resetted, okay. Until then it is going to count, okay, from 0 to 1 to 2 until 2 million it is going to count, and it is going to be resetted from there, right. So that counter value we are basically checking. If the counter value, if we haven't reached 1 million, we are going to keep the value as high, and once we reach 1 million, right, if we haven't reached 1 million, we are going to keep the value as high, and once we reach 1 million, we are going to keep it low. This combinational logic basically tells you that, right. Now as I told you that I'm going to basically incorporate these 4 duty cycles in the same design, so I'm going to use this switch, okay, and that is why I have written this always block, so that I can basically use this case statement, right. So case statement is the alternative for multiple if else statements. We have seen this as well in the previous videos. So I'm going to have this case statement. So if the switch value is 0 0, I'm going to map it to this 100%, okay. So that means that the duty, I'm going to set it as 100%, okay. So 2 million, right. Now if we have this at 2 million, the counter will never reach 2 million, right. Once it reaches 2 million, it is going to be basically it is going to be basically 0, right. So that is why this is going to be always true, and it will be one tick binary 1, okay. I will see it in the test bench. We'll verify this in the test bench as well. So this is for 100% duty cycle. Let me comment that. Let's map this 0 1 to 75% duty cycle. So for 75% duty cycle, we had calculated we need 1.5 million, okay. So alright, so I have made the mapping. So if we have the switch positions in these positions, we are going to have these different duty cycles, okay, mapped like this. So if we have both the switches as low, we are going to have a duty cycle as this, okay. So I have created this varied duty cycle so that we can see the effect on the board, okay. If we output just a single duty cycle, that we need to synthesize it again and again, right, for different duty cycles. So I have created this because I wanted to show you this effect, like varying effects of different duty cycles on the LED, okay, on the LED brightness. So that is why I have created this. So this duty will basically vary depending on what kind of mapping we set, okay. Alright, so we haven't assigned it to LED, so LED and PWM out is going to be same only. I've created this PWM out because I want to probe it as well on my analog discovery. So I'm going to map it to PMOD and I'm going to probe it and measure the duty cycle on the waveform software, right. We'll do that as well. Assign our LED same as PWM output, okay. End case we need to do. This is our code. Now we will create a test bench and basically verify it, okay. Let's have another module. Okay, this is not detecting the module, that is why it's giving a red line over here. I will see that in Vivado only. Okay, let's basically first define our time scale. I'm going to have time scale as 1 nanosecond and 1 picosecond. Okay, and I'm going to wait for this is going to go on for quite a long time, right? This is for 20 milliseconds, right? So I need to simulate at least for 20 milliseconds. We have written the test bench. Let's put the design and test bench in Vivado, and we'll create a project and we'll test this thing. Okay, so we have our clock running, we have this LED and PWM out. Okay, I need to run it for at least 20 milliseconds. It is automatically going to stop after 20 milliseconds, and let's see. As you can see, the PWM output and the LED, they are high for 50% of the time, and they are basically low for 50% of the time, right? I've simulated it for another 20, and you can see again the wave starts from here and it goes down after roughly 50 milliseconds. Okay, not roughly, exactly 50, 50% of the time. Okay, so 10 milliseconds. Okay, similarly we can also test this for 0 as well. Okay, as for switch is equal to 0 we can also test this. Okay, if you pay attention, there is a small mistake over here. See if you can notice. See, we are checking that if CTR is less than 2 million, then we are incrementing. Okay, that means if we are at 2 million minus 1, then also we will increment and we'll reach 2 million, right? But as soon as we reach 2 million, what is going to happen? This CTR is less than DUT is not going to is going to return 0, right? So therefore this entire PWM signal will go low, and it will go low for one cycle. Okay, if we see over here, if we run the simulation again, I'll run it for 42 milliseconds so that we have long enough time. And if you see over here, this is the PWM output, and it goes low for this period of time, one cycle, right? Again, if we see the value of counter over here, if you go into scope and objects, and if you select the DUT, you can take the counter out, right? Let's take both of these out, and I'll rerun the simulation. Again, I'll run it for like 42 something so that we have long enough time. And if you see now, if I go here and zoom in, let's change the radix to unsigned decimal, and you can see that it is reaching 2 million, and that is where this PWM out is going low. Okay, to handle this, what you can do is you can go here and you can add an equal to, so that this condition basically never returns 0, right? But that will be wrong over here because we are counting from 0, right? On the counter we are counting from 0, so we should not count up to 2 million. We should stop at 2 million minus 1, right? So in here, what you can do is you can basically write this as -1. Okay, and then also this should work because now the counter will only count up to 2 million minus 1, and the condition over here is if CTR less than DUT, right? So 2 million minus 1 less than 2 million, so that will always be true, and therefore we will have 100% of the signal always, right? That is one adjustment. If we had written this condition the other way, like in here, if we had written that the conditional CTR, if it is equal to 2 million minus 1, then set it to CTR is equal to 0, then it would have made a little bit of more sense. After we regenerate this simulation, we'll see what happens. Alright, now you can see that there is no one cycle dip in the PWM out. Okay, so this is our verification. The verification is done. Now I'm going to add the constraints, and I'm going to generate a bit stream, and then we'll see it on the FPGA. Okay, today I'm going to use Boolean FPGA board. Okay, not Nexus. So accidentally I set this to Nexus. Let's change that. see all this changing and getting the board files and everything, I have explained it in the earlier videos only, right? So if you want, you can check those out. This is clock. I have given the clock. I need to give the reset. Okay, we have two outputs. One is the LED output, so I'm going to use color LEDs, which is available on the Boolean FPGA. I'm going to use the blue LED, and last I need to feed the PWM signal to the P mode. Okay, so I'm simply going to add the P mode. Let's generate the bitstream. Alright, so the bitstream has been generated, and I'll put it on the FPGA and let's program the device. Okay, so right now you can see the LED is on. Okay, and the switch position is 0 0, so we should be basically getting a full DC signal to our LED. Okay, I have also hooked this analog discovery probe here, and we'll see it in the waveform software. So here when we go to from 0 0, if we go to 0 1, we are going to 75% duty cycle. So if you see, the LED brightness slightly has decreased. Okay, it's slightly decreased. If you go to 1 0, it is going to get more decreased than 0 1. Okay, this is 0 1. If you go to 1 0, it is going to be slightly lesser. Okay, and you can see it flickering on the camera probably. This is because of the frame rate thing that I've told you. The 50 Hz frequency is not high enough for the camera to not detect. Okay, and if you go to 1 1, it is going to basically be even more lower in brightness, right? So I'm going, this is 50%, and this is 75%, and this is 100% brightness, right? If I lock my exposure, you can see the brightness difference clearly, right? I'm going to go into waveform software over here, and let's basically have our scope. Okay, so I'm running the scope. So here you can see we are getting this perfectly DC signal around 3.3 volts, and if we make it 0 1, okay, you can see we are getting this kind of a signal. Now if I measure and show you from here to here, this should be around 20 milliseconds, right? So if you see, this is around 20 milliseconds, which is close to 50 Hertz. Now if I show you, the high time should be around 15 millisecond, right? So this is around 15 milliseconds, and this is the 75% duty cycle on 0 1, right? If I go 1 0, it is going to be 50 millisecond, 50% duty cycle, which is going to be 10 millisecond on period. So around 10 milliseconds on period is there. And if I go 1 1, it should be 25% duty cycle, so 5 millisecond on period, right? The frequency still is around 50 Hertz. Okay, so if you see, around 20 millisecond, 50 Hertz is there, right? So this is how we are generating this PWM signal. And if we had the frequency even more, this wouldn't even flicker on the camera as well. Okay, right now it is flickering on the camera, but in real life I can verify it is not flickering. Okay, at least to my eyes. Okay, so if you increase the frequency of the PWM, you can basically remove that flicker from the camera as well. Okay, so this PWM generator is basically implemented on the FPGA. Alright, so we have implemented this PWM generator on our FPGA board, and in this video we basically understood this PWM generation, what is this PWM signal and how we basically generate it. And the code that I have written is very simple, like it is very simple to understand. And now in terms of robustness, we can basically improve it, because right now if you see, the counter is increasing, and at that time if I change the switch, the behavior might be not predictable. So we can make the code more robust, but this code which should work, this is very simple, and this should work for most of the practical applications. Okay, and in this video we have basically implemented this PWM generator on the FPGA board, and hopefully you have understood everything. So thanks for watching.